Good afternoon. Thank you for being here today and for joining us for the Chancellor's Colloquium Distinguished Speaker Series. We are very pleased today to have with us Dr. Kumar Patel, a professor of physics and electrical engineering at UCLA, an inventor of the carbon dioxide laser. Dr. Patel will open with some prepared remarks, as we normally do with our series, and then he will be joined on stage by Dean Enrique Lavernia, who will talk briefly with Dr. Patel before moderating a question and answer period. I would like at this point to introduce our guest speaker and moderator for this evening, and I will start, of course, with our colleague, Dean Enrique Lavernia, who is going to be the moderator. Enrique started as a dean here in the College of Engineering in 2002, and with a two-year break when he served us as a provost, he went back to engineering from, in fact, 2011, and until today, he's serving as the dean there. Before arriving at Davis, Enrique was chair and chancellor's professor at the Department of Chemical Engineering Material Science at UC Irvine. He's a fellow of the American Association for the Advancement of Science, the American Society of Mechanical Engineers, the ASM International, and the Alexander von Humboldt Foundation. He has received many, many awards, and I'm not going to go through the extensive list. I will say the most recent one was the 2013 ASM International Gold Medal Award. Enrique holds a faculty appointment within the Department of Chemical Engineering Material Science at UC Davis, and he's there as a distinguished faculty. So Enrique, thank you so much for offering to be our moderator today. Now I'm very pleased, very honored to introduce our distinguished guest, Dr. Kumar Patel. Dr. Patel was formerly Vice Chancellor for Research at UCLA from 1993 to 1999, and is currently CEO and Chairman of the Board at Pranalytica, a manufacturer of technologically advanced gas sensing instruments and infrared laser systems based in Santa Monica. A professor of physics with a joint appointment in electrical engineering at UCLA, Dr. Patel invented the carbon dioxide, carbon monoxide, and the spin-flip Raman lasers, and pioneered the use of these and other lasers to measure trace gases in difficult environments. In recognition of these fundamental advances, Dr. Patel has been nominated for the Nobel Prize multiple times. He was at AT&T Bell Laboratories, now Lucent Technologies, for 32 years as Executive Director of the Physics Division and the Materials Research Division. Dr. Patel was elected to the National Academy of Science in 1974 and the National Academy of Engineering in 1978. He received the National Medal of Science given by the President of the United States in 1996. In recognition of the CO2 laser's importance to the medical field, he has been elected as an honorary member of the Gynecologic Laser Surgery Society in 1980 and 1985. He was elected as an honorary member of the American Society for Laser Medicine and Surgery. So it's great to have with us Dr. Patel, and I would like to invite him to come forward. Thank you very much.
Thank you very much, Chancellor Katehi, for that really glowing introduction. I hope I will live up to the introduction and walk you through some of the comments I want to make today before we go into the question and answer period. That should be showing my slide now, but okay, there you go. So what I want to do today in the next 15-20 minutes or so is to talk about a topic that's very close to my current activities, quantum cascade lasers. And what I want to talk about is how we took that particular type of laser from lab curiosity to a tool. Actually, what I really want to talk about is how to convert ideas into products. And I'm going to use the example of my company as a way to tell you about what we did wrong, what we did right, and perhaps during question answer period, you can ask me why we didn't do something right or we should have done something differently. So this is a case study of my company. We are a privately held company, and we did not start off as a laser company. We started off with a very lofty goal of having medical diagnostics through breath analysis, principally to provide care for individuals at a lower cost than what happens today. This was a very successful technology. We could measure parts per billion and some sub-parts per billion of variety of gases. We went through successful clinical trials funded by NIH. And being a sort of novice in the area of starting companies, realized that we had not lined up the customers ahead of time. I'll come back to that when I talk about what we did right and what we did wrong. But the short and the long of it, the short of it is that that particular market was very slow to develop, and we changed our market focus, not technology, but market focus, and found new potential markets for that technology that developed, that measured sub-part per billion levels of gases in air, or the pollutants in air. These were the semiconductor fab line people and the environmental applications. And this turned out to be very, very successful the technology penetration and market penetration. The thing that changed the company completely was a project manager at DARPA found out what we are doing in terms of selling commercial products that measured parts per billion level of pollutants in ordinary air. And so they pose us a challenge. If you can measure parts per billion of, let's say, ammonia or a sulfur dioxide, can you measure chemical warfare agents? Remember, this was a time about 2002, 2003. Saddam Hussein was supposed to have had a whole bunch of chemical warfare agents, and the idea was if we have our troops there, they will need help. So can you convert this technology for measuring subparts per billion of chemical warfare agents and explosives? We showed it could be done. Basically, we modified what we had at that time, is a carbon dioxide laser-based instrument to measure chemical warfare agents. DARPA being what it is, they were not satisfied. What they said, look, what you have is an instrument that weighs 175 pounds. A soldier can't carry it. Make something which is only 20 pounds. And so that's what brought us into quantum cascade lasers, because that replaces the CO2 laser which weighs 60 or 70 pounds with something that weighs 2 ounces. So that turned out we were quite successful there. And of course, as DARPA always does it, they said, you know, that's good, but we have a much more difficult problem now. These terrorists have acquired shoulder-fire missiles, and they are firing these weapons at our aircraft in Iraq and in Afghanistan. So we need a different kind of laser, much more powerful laser, and can you develop that? And so the ultimate outcome of all of this was that while we started off as a company that was going to change the medical diagnostics, we ended up doing something completely different, very successful, but now we have come 180 degrees around and we can apply the same technology to our original sensor. So let me say a few words about what the company does, what quantum cascade lasers are, because if I'm going to tell you why they are so good, you should know at least what they are. So what I've shown on this slide are two different kinds of lasers. I think all of us, most of the people are familiar with the laser that is shown on the left-hand side. Don't worry about the details. That's the kind of laser that goes into a handheld pointer. Typical color of the handheld pointer is red, sometimes green, but it is in the visible region. once that particular material is built, that particular laser is defined, you can't change the color. For different colors, you need different composition of materials. Quantum cascade lasers are completely different in the sense that you don't change the materials. What you do is you change the thickness of various layers. So on the right-hand side is a artist depiction, my depiction of what a quantum cascade laser is. And so what you find is, this is the only time I will invoke quantum mechanics. When you put a particle in a very small box, it can no longer move with continuous velocities. If, for example, if I were to move from here to there, I can move with any speed that I want. But if I have a particle and put it into a small enough box, I can move only with certain fixed velocities. So what that does is it creates distinct energy levels inside for the electrons. Transitions between this give me laser radiation. And you change the spacing between this is by changing the thickness. If I make the particle box small, the levels become farther apart. If I move them farther apart, the levels come closer. So there is a very, very convenient way of changing the energy of the photon that comes out. The only unfortunate part is that that system works only in the infrared region at wavelengths longer than maybe 3.5 microns. But that's not all that bad, because that's where some of the most important, most interesting scientific and technological questions lie. Apart from that, many of the practical applications, such as defending airplanes from shoulder fire missiles, lies there. So in a sense, that is a different kind of laser. Again, I won't go through the details, but what we brought to the table, that laser was invented in 1994 at Bell Labs. Now, my claim to fame is not having invented the laser, but having hired the guy who invented the laser into Bell Labs. So in this particular case, my claim to fame is that I identified a genius. Be that as it may, when we got started on the DARPA program, as I said, the quantum cascade lasers were laboratory curiosities. You could buy one, but you had to have half a dozen PhDs hanging around to make this thing work. Clearly, that's not how one makes an instrument, makes it a practical device. And so our contribution, my company's contribution, was to take that device, a tiny device, something less than 1/10 of a thickness of a hair, maybe 5 millimeters long, and convert it into something that I can package in a box, give it to you, and all you got to do is to turn the switch on, and it'll work every time. That's what you need to be able to do if you're going to use any kind of technology, any kind of new idea, convert that into a product. So message number one, technology is great, but there is a long path between technology and a product that's going to make anybody any money. What my company did was we changed the original design of the laser completely, to the point where we have now fundamental patents which allow us to make the best quantum cascade lasers anywhere in the world. This is what we are able to do: highest power, highest performance lasers. And this slide shows the kind of things that we have been able to do. And there are a couple of wavelengths listed. Wavelength describes its color primarily. Again, to remind you, wavelength of what we see as light that we see is roughly 0.4 micrometers to 0.7 micrometers. These lasers, let's say at 4 microns, it's 10 times as long a wavelength. You can't see it, but if you are irradiated with a light beam, you'll feel heat. So this is what's called infrared. And the first two wavelengths, 4 microns and 4.6 microns, are important for protecting aircraft from shoulder fire missiles. The other wavelengths are important for detection of chemical warfare agents and explosives. So we have a whole range of wavelengths that we are able to make. The key point here is the power output. Now, this doesn't sound like a whole lot of power output compared to another one of my favorite lasers, the carbon dioxide laser, which a box maybe of this size will produce several hundred watts of power output, but it will weigh 200 pounds. And as I said earlier, what you really want is something very light. So power is lower, but it comes with many other advantages. And some of the advantages are listed here. This is what I've tried to do here is to give you the reason why this laser, which was first made to operate in 1994, first commercially available laser was 2006. We were the first ones to brought it to the market. Why in a very short period of time, it has become, I wouldn't call it the best thing since sliced bread, but pretty close to it, very close to it. So what this slide shows is comparison with what else is around in this particular wavelength region and why this really makes sense. The most important thing, without worrying about what the different lasers to optical parametric oscillators, to CO2 lasers and everything else, either they are bulky, either they are heavy, or they require another laser to make this particular type of laser. So by the time you go through all of this chain, you have lost a whole bunch of efficiency. Efficiency of converting electrical power into optical power is very low. For any kind of application, you need high efficiency. And so quantum cascade lasers, one, they are direct, electrically pumped, they're solids. Once made, and if it works, it'll work forever. There is nothing to wear out. Unlike in a carbon dioxide laser, the gas mixture may have to be replaced after a few years or what have you. If it falls down because it may go out of alignment, it'll break. This is incredibly rugged. Covers a very broad wavelength region from 3.8 micrometers to longer than 12 micrometers. Everything that you want to do can be done with this one particular laser. So the thing that I was talking about was taking something like this from a laboratory curiosity to a tool. What's required? First of all, it's got to be air-cooled. Nobody wants to carry around liquid nitrogen with you if you're making an instrument. Should have a single point power supply so that people don't have to fidget with the power supply. Just flip a switch, it should work. There should be a clean and logical human interface so that the user sees exactly what's happening. And most importantly, it requires very, very high reliability. So if I take all of that, if I do all of that, even then there is something else that comes into picture. How can I, if you are a customer, how can I convince you that you should buy this particular type of laser as opposed to something else? So here are some of the requirements. You need to have high power, obviously, because without power you can't do anything. Room temperature operation. Need to have high wall plug efficiency, efficiency of converting electricity into photons. Should have good beam quality so that I can project the beam over very long distances. Should have good beam stability so that once it is designed, the beam won't wander as the laser ages. Should have high reliability, long lifetime, and ruggedness. If I'm going to put one of these lasers on an airplane or a helicopter, it is subject to a lot of vibrations, a lot of shocks. Should be able to work. Without going through details, we have tested our lasers up to 1100 Gs. 1100 Gs is a shock 1.5 times that you'll have if this laser was sitting on a top of a gun and you fired the gun. So in a sense, this laser now is qualified not only for mounting on a rifle, for example, but also going on the rockets and everything else. So the question is, what do some of these systems look like? So on the top right-hand corner is a typical system. If you are a customer, if you're a university researcher in defense establishment, this is what you would buy: a laser package, which sits here, and a power supply. The power supply, the front face tells you what the laser is doing. You flip a switch. Every time you flip a switch, it works. But for industries like Northrop Grumman and BAE Systems and Lockheed Martin, they don't want to buy this whole thing. What they want is something which is, they can just take the laser itself, build their system around it, and so this is what goes inside that box, what you see here. Its package volume is less than 50 cubic centimeters, and the weight is less than 100 grams. That produces 5 watts of power output. And so that's, in some sense, in this wavelength region, that's the highest amount of power output per ounce, if you want to call it. There is another application. What you see here is is a big box. We have seen laser pointers that people hold in hand. There are similar pointers, similar applications in the infrared. Again, fortunately or unfortunately, these are all defense or homeland security applications. What you like to have is a little pointer that you point at that glass which is sitting there and be able to say what's inside the glass or what's outside the glass, is it dangerous or not? This is for detection of improvised explosive devices, the things that kill the largest number of people in Afghanistan today. Somebody leaves a package by the side of the road, which is detonated either remotely or by some kind of proximity fuse. And you want to be able to tell what it is before a soldier goes there and tries to examine it. So you need something portable, light. And one of the things we found was that these lasers can be made very small, will work at room temperature with very high wall plug efficiency to the point where one can make a broad range of products. So some of the products that we make, and I'll say a little bit more about this thing in the middle here. That's our smallest laser that anybody has made in this particular wavelength region. The whole thing weighs less than 2 ounces, produces 4 watts, requires 12-volt battery power to power it. So this is the bottom line. It works at 10% wall plug efficiency, which implies that if I had 2 AA batteries, actually I need 4 AA batteries because I need 12 volts, but enough batteries, 4 AA batteries will run it for several hours at 2 watt of power output. Something that a soldier needs to have in his hand, because he can't constantly go around changing batteries, nor can he recharge the batteries. The long and short of that is that now we can make instrumentation which can be very compact. Here is what we call a standoff explosive sensor. The example I gave, I see a briefcase sitting 50 meters from here. I'm supposed to find out whether I should approach it or not. If I go close enough, it'll probably explode and I'll be killed. And you have seen that movie, The Hurt Locker, where there is a physical object there. Should you go close to it or not? We have now developed an instrumentation that you see there. The rectangular box contains lasers. The big tube that you see, which is basically empty tube, has a telescope which looks at the object that you want to interrogate. Sends out a laser pulse, and what comes back brings back with it information about what is on the surface of this physical object. And this instrumentation was tested at China Lake. China Lake has a very large naval facility where you can have explosives out in the open to see how well it works. It worked exceedingly well. It's fairly small. This is how it is used. A person can hold it on the shoulder. It's roughly 20 pounds. And basically a soldier can carry and make things happen. So starting from a company which was going to do one thing, we have completely come around to making something else, which is of enormous value in these days of what I call global terrorism, where we can help the country do something of value. So there are a number of applications. Let me skip past that point. And again, I think, as I said, what I really want to focus on is what have we learned out of this? What have I learned out of this exercise? Converting ideas into product. So if this is what we want to do, I have an idea, I want to convert it to product, what do I need? So first of all, you have to have an idea. You don't have to have an idea. If somebody else has an idea, identify a good one. Makes no difference where the idea came from. The important thing is identify a good idea. The second most important thing is match the new capability with the potential opportunity. Having just technology by itself isn't going to do anybody any good. And most importantly, recognize what you need to take it from an idea to a potential product. Resources, which is people, money, and infrastructure. Next thing is you need to convert that into opportunity into solutions, because the customer does not buy technology. Customer has a problem, and he or she is looking for a solution. And you have to be able to match what you are providing with order to solve the problem. And as I've been saying over and over again, technology is not the same as solution. You need to identify customers early, long before the product comes to the market. And if something goes wrong, you should be sufficiently agile in changing direction if necessary. So now the question is, did we do it right? So here is what I call my scorecard of good and bad. My scorecard of good and bad is idea. I think it was a really good idea, non-invasive medical diagnostics. I mean, I think, I can't think of anything better technology can bring to the people. It's a great problem. There is a great market opportunity. We have an aging population, need to contain medical diagnostic costs, and you need real-time diagnosis. If I can tell you that you have potentially liver problem while you are still in the office, while I'm carrying out the test, I can do something very quickly. You don't go away and forget about it, not come back 2 weeks later to find out what's wrong. So clearly, having real-time diagnostics has enormous value. We were able to line up resources. We succeeded in attracting outstanding people and raising capital. We also got NIH funding for carrying out the extensive tests, clinical tests. So we did convert good R&D into a good product. Now comes the bad part. The bad part is we did not speak with the customers early enough. Customers in this case being physicians, dialysis centers, hospitals, etc. What we found out that these people don't buy instruments. They want to lease the instruments. Now for a startup company, where am I going to get the money from to build these instruments? Because by the year 2002, all the venture money had dried up. Remember, that was the post-internet bubble explosion, and then there was no money to be had. And so what did we do? So what did we do to recover? I mentioned some of that. Agility, we changed our market focus. At that point, we certainly realized that speaking to the customers was incredibly important. We found new customers, found out what they wanted, modified our instruments to make that happen. And that clearly worked out very well, semiconductor fab lines and environmental agencies. The thing that changed for us completely was we found new angels. DARPA, I just mentioned, DARPA found us. Most importantly, I found several ex-Bell Labs people in DARPA, which was clearly of enormous value. That having credibility with somebody who has money, that has enormous value. And they posed us a very tough problem. Tough problem was convert a 175-pound instrument to a 20-pound instrument. I didn't tell you that we didn't succeed. We came down to only 40 pounds. But they were happy because at 40 pounds you have lost an enormous amount of weight. And their view is the next iteration will get you down to where you need to be. And as you saw on the last slide, the next iteration did get us down to 20 pounds. What that allowed us to do, that forced us to do, was to change our technology focus, getting away from CO2 laser-based systems to quantum cascade laser-based systems. And as I mentioned, at that time, QCLs were still laboratory curiosity. In 2 years, QCLs became practical lasers for a variety of applications. And as I said, now at that point, angels came back with newer problems. As I said, the problem now is protecting aircraft from shoulder-fire missiles. And new customers, defense and homeland security. What's so good about them? For them, security matters. Money is not the problem. Problem is making sure that an airplane that costs $200 million doesn't get shot down. And so the equation has changed. I still am looking for those applications where we can insert quantum cascade lasers into a very large volume market. I think we have found one. It's still a very nascent market. This is measuring carbon dioxide concentration in a variety of situations within a hospital, especially for patients undergoing surgery. Carbon dioxide measurement is the critical way by which you can determine the health of the patient. And so to be able to do this in real time, every single breath by breath, it is going to be very important. So what made the difference? The things that made the difference was agility in technology, agility in marketplace, agility in customer focus. we had to change our number of people, the kind of people we had completely. We've hired the best QCL technologists, and that has allowed us to become the finest supplier of highest performance QCLs in the world. With the help of DARPA, we are able to find new customers. And one of the things that I find somewhat less than satisfying is agencies like an NSF, great agency, but they don't have the connection with the real world. A project manager there cannot and doesn't have the capability of understanding what will happen if this research area was successful. There's got to be a chain, that you got to have different things that happen at different times. Not that everybody should become an applications person, but at least you have some idea so that you can point you to somebody else to make something happen. Customer focus is clearly important. I think the bottom line is we realize that customer is the king, and that this has now happened at every level of the company, because the customer makes payday happen. There is just no substitute for that. We still publish in the best journals, but we never lose the central notion: don't lose a customer, because if you lose a customer, he'll never come back, he or she will never come back. And there are two parts to it. Unlike doing R&D, where the results that you promise to an NSF, DARPA, or whatever it is, are on a best effort basis. You're going to do your best to get to that point. But if you're selling a product, that doesn't work. Customer has paid you for a particular performance, and you better meet that. Not only that, but you better meet that. You better meet it on time. Because a customer who walks away because you missed the deadline of delivery will never come back. If you provided with the customer with a slightly lower performance QCL, lower performance device, they'll be angry at you, they'll come back, they'll make you fix it, but they won't walk away. So never miss a deadline. So something very difficult to teach to young people, PhDs who come out of university. Deadlines are very important. So here is my final question to you. You be the judge. Did we do it right? Could we have done it better? Could you have done it better? And so with that, I'll stop here and respond to any questions that you have. Thank you very much.
Thank you, Dr. Patel, for that very interesting lecture showing the evolution of technology and Pranalytica. And again, on behalf of the entire Davis community, I'd like to welcome you and Sheila to our Davis campus. Great to have you both here. I'd like to go back to your own life, if I may. You were 19 years old when you earned a bachelor's degree from Pune University in 1958. A year later, you obtained a master's degree from Stanford, and 2 years later, at the age of 22, a PhD. So clearly, you grew up with a passion for academic research. Where did this come from?
Well, I've never thought patience was a real virtue, and I think if you want to get something done, you better do it now rather than tomorrow. So that's one. Number two, living on a graduate student's stipend was not great fun, and wanted to have some real money so that I can do something with it. So getting out from Stanford early was a good thing to do. But as all stories have a different sides to it. Something that clearly that I'd met Sheila the first day I came on the Stanford campus, and didn't want to get married until I could support myself and her. So that was also important.
Fair enough. Thank you. Now, you joined Bell Labs in 1961, and in 64, only 3 years later, you invented the nitrogen carbon dioxide laser. Tell us about the famous note that you left your assistant, Rudy, at 2 a.m. one morning when you obtained 3/4 of a watt power output from the prototype laser, and why was this significant?
Okay, so I think the one of the things that drove the development of carbon dioxide laser was the fact that first laser was operated in 1959, and if you remember, some of you probably remember article in Scientific American. The outside cover had this, what can best be described as a predecessor of Star Wars pictures, lasers shooting at all kinds of things and all kinds of wild things happening. And yet, by the time 1963 came along, lasers were still what I call milliwatt devices. If you put your hand in the beam, it's not going to hurt you. And so clearly there was a big move towards getting higher and higher powers. An interesting anecdote about that is that I was at Bell Labs. There were probably no less than 40, 50 individuals, PhDs, working on different aspects of lasers. And all except one, they were all working on solid-state lasers. And the idea being that solids have much higher density of whatever you want to work with. So in the end, that's going to produce the highest amount of power. So there's a minority of one, that's me. Didn't quite believe any of this, not because that was right or wrong, but because what most people forgot was that while you have much higher density in these solids, there is also a problem of removal of heat. And solids are not exactly friendly places from where you can remove heat. Gases are a lot better. I can flow the gas at enormous speed, take away the waste heat. And so it just so happened that my limited knowledge of quantum mechanics could allow me to do calculations only on a carbon dioxide molecule. I can't deal with anything more than three atoms. And so that's what we started with. That's what I started with. And surprise of all surprises, the first calculation showed that it should work very well. How did I do the calculation? Remember, this was before computers. I had one of these old Freedom calculators, which sort of went clanky, but the calculation showed that it would work. And the first night I turned it on at 2 o'clock in the morning. Something happened. What happened was there is those of you who know how to measure power output, you put a power meter to see how much power is coming out. And so the needle on the meter goes to the maximum. I said, there is something wrong with the power meter. I said, throw it away. That I'm going to put my, how can the first time you turn it on, it can work so well? Come on, it's just sort of, it's counterintuitive. So I put my hand in the beam. It's the biggest mistake I made. I got a really bad burn. The first example of unintentional surgery. At which point I knew that there was a lot of power coming out. And one of the great things about looking for solutions rather than looking for technology was this is 2 a.m. 2 a.m. I know there is a lot of power. How do you measure it? Well, you got a beaker of water, a thermometer, stopwatch, and calculate what the temperature rise was after a few minutes, and that's how you measure power. Of course, that's the most basic and fundamental way of measuring power output. But there was a fun time because I went home, left a note for my assistant saying this is what had happened, and so the instructions for what to do next. And I think from then on to the time we made the first 100-watt laser was, I think, maybe something like 4 months. And at which point it became clear that I will not be able to do that work any further because that work was then picked up by the U.S. Army, and the activity there was classified. I was on a student visa, and so couldn't possibly get any access to that. So while I'm talking, I'll tell you another story. Stories are fun. So in late 1965, the news had reached AT&T, the parent company. Something of real value had happened at Bell Labs. This is the guy who's making holes in wood blocks and things of that kind. So about 6 senior vice presidents from the AT&T came by to see what was going on, and so showing them around, and have this with the mirrors you direct beams at wooden block, and with the ceramics and everything else, it glows very bright. Pretty soon I smelled something burning. One of the vice president's tie had been cut into exactly into two because there was about 5% reflection from something which, that he just happened to be in the path. And so now here I'm 26 years old, student visa. I said, here goes my career at Bell Labs in flames, literally. And so I apologized to this man profusely. I said, I'm really sorry it happened. He said, not to worry, this is the best thing that has happened. I'm going to take that cut piece of tie back, frame it, and tell people from FCC, because they always used to badger AT&T about why are you spending money at Bell Labs. And I said, I'm going to show them what great things have happened. So I said, my job is saved. Incidentally, he did frame it. That I happened to see him several years later, and it was in his office. Tie cut into two, with an inscription at the bottom which said, "Great things happen at Bell Labs."
Well, that's a great story, and I guess we're glad you did not have access to a more powerful computer.
That's right.
Now, you became this new laser's staunchest advocate and looked for new applications for this device with many impressive applications. And today, I think there's more practical uses for the CO2 laser than any other type of laser. So can you tell us about a few applications you did not expect that you were surprised by?
Okay, so I think the most obvious applications are clearly materials processing and surgery. They are very widely used. You cannot buy a automobile today whose white body is anything other than an engine, is not welded using either CO2 laser or some other type of laser, but mostly CO2 laser, because it is a lowest cost per watt laser that's around. Things that I did not know, and I think this is the most unusual example of this was, I hope nobody smokes here, but the cigarette companies make tiny holes in the filter all around so that when you inhale, fair amount of air gets in there to reduce the concentration of smoke that you inhale. Those holes are drilled by using a CO2 laser. So that's one application that I didn't think of. Second application which I thought of but never made money was some years later I came across unprocessed macadamia nuts. Now, I don't know if you have seen a macadamia nut in a shell. It's an incredibly hard shell, very, very difficult to open. So I said CO2 laser would be the ideal thing to do that. And so sure enough, I tried it out. It works beautifully well, except that it's not cost effective. What I missed out on was the use of CO2 laser for peeling potatoes. Now, this, and a very, very important application for Campbell Soup Company. Campbell Soup Company yearly uses upwards of 10 million pounds of potatoes to make it into various soups. The way potatoes were peeled with a blade, you lose roughly 5 to 7% of the meat. Out of 10 million pounds, that's a lot of potatoes. So somebody figured out what you need to do is to take a high-power CO2 laser, flash it. What happens is the color of the skin is different from what's inside. Outside blows off, and that's it. And you got potato without skin left behind. So didn't think of it.
Fascinating.
Now, had I thought of it, I would be rich beyond my imagination.
I thought you were going to tell us that you could open the macadamia nuts and roast them, but no, that. Now, during your early years at Bell Labs, you enjoyed the research-rich environment in the United States when in the 60s, our government, who was reacting then to Sputnik, poured a lot of resources into education, into research, particularly engineering and physics. It was a great time to be a scientist, undoubtedly, because I think the country believed that technology could be used to solve problems. Today, we seem to have lost that knack as a nation for investing in technology. What, in your view, must we do to reignite that passion for using technology to solve problems?
Okay, so I don't think the country has lost the understanding that technology will solve problems. I think the probably an underlying issue here is we have enough technology to solve the problems that are at hand. What people don't understand, and I think that's something that politicians and people who make budgets need to understand, is that today's tools will not solve tomorrow's problems. And tomorrow's problems are always going to be different. And for that, you need the next generation of well-trained, well-educated people. And if you don't have an infrastructure that supports research, development, experimentation, you will not be able to find the best people to carry out that activity. And the day you lose best people, you're lost the game. So I think it's not so much that people don't want to invest, but there is a belief that there is more than enough today to solve today's problems, which is probably right, but that doesn't address a central issue. Tomorrow's problems are going to be different.
Now, going back to Bell Labs, you rose rather quickly through management. In '67, you once explained that as a Bell manager, you were judged not on the basis of your own past accomplishments, but on your ability to hire people who were smarter than you were, which must have been really hard. But clearly, you were an amazing judge of talent, because 6 of the people you hired at Bell Labs went on to win Nobel Prizes. What was your secret?
Well, there are, at Bell Labs, either I hired people directly or I nurtured them. I think 7, maybe 8 people in that category got Nobel Prizes. I don't think there is a record that's matched by anybody else at Bell Labs. But it has less to do with me and more to do with them. Because I think the identifying people with imagination, people with curiosity, that's what you need. Anybody can do his or her PhD dissertation over and over again very easily. But very few people are able to ask questions like, what if? What's the next step that I need to take to do something better? And many of these people fell in that category. When they came to interview, instead of telling me what they had done, they would ask me, what are the most important problems? I mean, where is, I've been a graduate student for the last 4 or 5 years. My vision was limited by what my professor asked me to do. I'm going out into the real world. Tell me about where the hottest areas are going to be, not in terms of technology, but problems that need to be solved. Because problems that need to be solved focus your research, your development, your experimentation. And that was, in some sense, that was a real strength of Bell Labs. If anybody believes that Bell Labs carried out blue sky research, it's just not true. Yes, it did carry out blue sky research, but it was guided by an overall desire to have technology developed which eventually meets the needs of AT&T. Sometimes they miss by a mile, like in development of CO2 laser, but then they made up by collecting royalties for many years. In other areas, what came out went directly in the communications technology. But if you don't have that breadth, you can't focus on what you have in the middle.
Now, the spin-flip Raman laser, which you invented in '69, allowed you to conduct high-resolution spectroscopy of molecular gases, which in a sense made you a pioneer in the field of atmospheric pollution detection. You supplemented this work in '73 by measuring the stratospheric nitric oxide, and the data brought to the nation's attention the problem of ozone depletion by man-made nitrogen oxide emission sources. All these years later, atmospheric pollution continues to be a problem. So have we failed to pay sufficient attention to the data that you started generating so many decades ago?
It's a good question. I don't know the answer. I wish I did. But I think the in many ways, if I come back to the spin-flip Raman laser, it's a great technological achievement. It has zero commercial value. And you know, that sort of goes to what I mentioned earlier in this one of my slides. It's got to be operated at room temperature, should be light, should be highly efficient, and met none of those requirements. What it did was it did do something of value for a limited period of time. And that, in some sense, was very important because we already have a problem with depletion of ozone layer. Can you imagine what would have happened if, and I hope I'm not insulting Boeing here, but if there is no Boeing employee, if Boeing had succeeded in putting their version of SST into service. It was supposed to have flown roughly 30,000 feet higher than where the SST flew, the Concorde flew, would have dumped a whole lot of nitric oxide in the stratosphere, just at the worst place. And we provided measurements, actual measurements in stratosphere, which showed that nitric oxide would be a real disaster. And you know, then I'd like to say that sort of, in some small sort of way, we are instrumental in preventing that from happening. I don't think Boeing will appreciate this, but I think that there was a wrong solution for a wrong problem, and being able to measure nitric oxide in real time in the stratosphere was what sealed the coffin.
Now, in 1993, you left Bell Labs and became Vice Chancellor for Research at UCLA, a position that you held for 6 years until '99, and you continued to teach physics, astronomy, and electrical engineering at UCLA. What made you transition from industry to academia?
I'm sorry.
What was the driving force for you to transition from industry to academia at the time?
Well, you know, I'd been at Bell Labs for 32 years. I could have plotted exactly how things would have gone from then to my retirement would have occurred in 2003, because 65 was the absolute retirement age. And what I saw did not appeal to me. It was a good time to do something different. Still reasonably young. Going to a university was the only other option, and I took it. UCLA was a good place. I shouldn't say was, is a good place. It still is a good place. I don't want you to go and tell the Chancellor that I said it was a good place.
We'll get you a faculty appointment at Davis if she does.
No, and I think the best thing that happened in some ways is my stepping down and returning to the physics department as a professor, because that's what allowed me to. Is this thing working? Yeah. That's what allowed me to contemplate starting the company, because in some sense that is now my third career, and I'm truly enjoying it. Enjoying it not because there is a potential for making money. That's small part. The real part is I'm able to do something here that I could not do at Bell Labs. Bell Labs, with many of its positives, had this absolute, I wouldn't call it absolute, but pretty close to absolute boundary conditions on if the research people, somebody working in the research area, can take that technology to make a product, to make it get in touch with the customer, because that the notion was there are other parts of Bell Labs who are responsible for development and subsequently taking to market as a product. You know as well as I do that there's something called not invented here syndrome, and that worked in Bell Labs just as well as it works almost anywhere else. And so what I missed out on was this continuum of activities that takes you from research development to a product. I can do that now, and I think I've enjoyed it a lot. And the most important point is young people that I've hired, that we have been able to hire, enjoy it too, because even though they came out directly from university with only research background, they see the excitement when they sit in front of a customer and tell them, this is what you have made, this is what your product is coming out. And the guy or the woman says, that's exactly what I want. And their face lights up. I mean, there is nothing like a feedback in terms of what the contribution you have made to solving somebody else's problem.
Now, your many awards include the President's National Medal of Science, which President Clinton presented in '96 for, and I quote, fundamental contributions to quantum electronics and the invention of the carbon dioxide laser, which have had a significant impact on industrial, scientific, medical, and defense applications, end of quote. Just this past May, in fact, you were inducted into the National Inventors Hall of Fame. Which of your many honors has pleased you the most, and why?
So that's that's a good question, because you remember the most recent one the most, right? No, more seriously, I think the two that stick in my mind. Clearly, getting the award from President Clinton was a highlight. Had it been any other president, it would not have quite that memorable, because Clinton is a memorable person. He's an incredible human being. Again, I'll tell a small anecdote. 2 years prior to that, when UCLA celebrated its 50th anniversary, Bill Clinton was a speaker, and I was the Vice Chancellor for Research, so he shook hands with everybody. And in the White House, when we were there he came by to greet everybody before the ceremony. Yeah, I told him, Mr. President, you probably don't remember me, but you shook my hand at this occasion. And he looked at me straight in the eye and he said, what do you mean I don't remember? You are the fourth person with whom I shook hands, which is absolutely correct. There is no way his aide-de-camp would have reminded in terms of where I was. So he clearly has absolutely fabulous memory. He's a people person. I had a small memento for him, which I gave him, and he holds it in his hand. The aide-de-camp says, Mr. President, can I hold it? He says, no, he gave it to me, it's mine. And so, it's when you are in his presence, regardless of how many people are around, he makes you feel you are the only person in the room. And I think, and Sheila, my wife, saw the same thing. She had never met him before, and he carried on a conversation with for a good 10 minutes. And he's just absolutely amazing individual. I wish he had run again. He could have run again. He could have been elected president one more time. So let me just continue on this vein a little bit more. The last award, which is the induction into the Inventors Hall of Fame, I think that was a great occasion, not because I was there, but because who else was part of that process. And one individual that I remember, and how can I forget? Apple founder Steve Jobs was inducted at the same time, and so that's called being in a very good company. And as they say, people are known by the company they keep.
Thank you, Dr. Patel, for sharing those inspiring thoughts of your personal and professional life. Let me now open it to the audience. I believe we have microphones, so if you raise your hand, somebody with the microphone will come over, so please.
I was wondering if you could comment on your uses of the research that you've done in the gynecological area for gynecological medicine, and if you see any use of your CO2 lasers in targeted therapies.
I'm sorry, could you ask the question again? I'm really hard of hearing, so you have to speak a little louder.
I was wondering if you could comment on your use of your research in gynecological medicine. And second, if you see any possible uses of your lasers for targeted therapies.
Okay, so this is, I presume you are talking about the quantum cascade lasers. Okay, so here is something which I think is going to happen. Typical laser surgery involves evaporation of the water in the tissue to do the cutting, which means there is a fair amount of heating that takes place. There are good reasons to believe that collagen, the thing that binds the skin, the underlying thing that keeps the skin together, has this resonance around 6.45 micrometers, where you can use much lower power laser to make a incision without burning or cutting. And it has been shown to happen, it has been shown that one can do that. Unfortunately, the laser that was used earlier for this particular demonstration was a free electron laser. Typical cost, $500 million. And you have to go to the instrument as opposed to the instrument coming to you. And we are actively looking for potential ways by which a 6.45 micron quantum cascade laser, something that surgeon can hold in his hand, can do the same thing. If it can be done, it would clearly absolutely revolutionize substantial part of surgical procedures, because it is not cutting, it's really changing the molecular structure of collagen at that particular point. Apart from that, the longer wavelength lasers are clearly now being incorporated into sensors for what we initially started with, which is use of non-invasive diagnostics of disease. And we are going back there again. Now that we have quantum cascade lasers, we can replace the CO2 lasers, make the instrumentation smaller, hopefully cheaper, and hopefully much more widely available.
We had some other questions over here.
Hi, I'd like to thank you for entertaining us on this Tuesday night in Davis. My question has to do with the National Ignition Facility, and it's sort of controversial whether it would continue to be funded. If you had the decision to make that, whether to continue to fund it, would you, and why?
I'm sorry, what was the question? Could you? I'm sorry.
The National Ignition Facility over in Livermore?
NIF, the National Ignition Facility.
National Ignition Facility. I think the. Okay, so here is my problem. I want to answer that question, but I can't answer the question. I'll tell you why. Because I'm part of a study that is being carried out by the National Academy of Sciences as we speak about the quality of science and engineering at the 3 national laboratories. And so anything I would say would one way or other jeopardize what that report is going to say. But it is in fact an excellent facility. I have never seen better deployment of technology anywhere in the world. I mean, this is just absolutely most fabulous thing that you can ever see. Whether it solves the original problem or not, that's really not relevant. But I went through my discussion. We started off solving one problem, ended up doing something else so much better that the initial problem really was not important. So clearly, if you have a good tool and good people in charge, they'll find the right use for it.
I'm interested in the QCL technology, but it's not my area. Currently, QCL people are working a lot to decrease the frequency into terahertz, but now you still need cooling facilities. So may I ask Dr. Patel, from your vision, is that possible that QCL can working at temperature to generate terahertz frequency, like in the range of less than 10 terahertz? It is possible or not, or is there some fundamental limitation to increase the temperature of QCL to working at terahertz frequencies?
I'm sorry, I really have a problem understanding. I mean,
Okay,
I'm
so
deaf.
let me make it more clear. So QCL has been active research for terahertz generation, terahertz sources. Terahertz. Is that clear?
Terahertz. Terahertz? Terahertz.
I'm sorry.
It's a frequency, 1,000 gigahertz.
Oh, terahertz. Okay, I'm sorry. Thank you. Okay. Okay.
Sorry, my accent is
No,
too strong.
it's not your accent. It's my hearing. Okay.
Yeah.
So the as I mentioned, the wavelength of what comes out really depends only on the thickness of the layers, and so it is possible to make terahertz lasers out of QCLs. They work reasonably well, but none of them work at room temperature yet. And until that happens, it is unlikely that they will become part of any application other than laboratory application. And I think there are good reasons to believe that that will happen. But as many of my material scientist friends will tell me, improvement in materials quality is not something that cannot be dictated. It just, there is technology innovation that keeps on taking place, and maybe a year from now, maybe 5 years from now, we will have terahertz lasers. And I think there are many really good applications of terahertz lasers, and there are some really bad applications. Bad not because it doesn't do good, but it's really totally inappropriate. For example, terahertz lasers are touted as being the best way of detecting chemical warfare agents. It's just not true, because terahertz radiation will not propagate through air any distance, because anything that's around absorbs in the same region.
I see. Thank you. May I ask another question, since you mentioned terahertz applications?
Sure.
From your vision, which application you think is most useful in terahertz? Or which applications, if you have more?
Okay, so the applications which are going to be most useful is something that sees below, through the clothing. And for example, the airport applications for screening, detection of if the person is carrying a metallic weapon or a pouch containing something which has a much higher molecular weight than human body skin. It's going to be of some value, because it is something that you can't do many other ways. You can do, of course, you can use backscatter X-ray to do that, but I'm not an expert in the area of X-ray, so I can't tell whether it's really good or bad. But I do know that terahertz radiation will not hurt you.
Okay, sure. Okay. Thank you.
Other questions?
Yes, if you were to advise an 18-year-old who's scientifically oriented, what major would you advise? Would it still be physics, or would it be something else?
Okay, so a very good question. I think I don't know what I would say. I think the bottom line is, when I was 18-year-old, actually I didn't have too many opportunities. I knew what I was good at, and being in India, if you had technical education, you probably had a reasonably good chance of supporting yourself for the rest of your life. I think that's probably still true, but I don't know how true it is. I don't think that's true in this country anymore, because my pet speech, we don't value technologies as well as we value people who move money around, namely the people in Wall Street. And so clearly, if I were to give somebody advice, an 18-year-old advice, what would I do? I would tell them, get a technical degree, but don't spend your life being a scientist or an engineer. A terrible thing for me to say, but I just don't know how in good conscience I can ask somebody to do something different. Of course, the correct solution is, that's not the correct solution. The correct solution is the society needs to hit the reset button and figure out what's important and what is not important. If solving tomorrow's problem is an important thing to do, we better put our money and our, more than money, our emotional capital behind it. We don't seem to be able to do that. We seem to be able to give $25 billion to some guy, some person who has moved money around on Wall Street, has built off 1,000 people off a lot of money. What happens? Either the person goes to jail or doesn't go to jail. But all of that's irrelevant. You have sent a message to the young people how to make money. So the message here is, if you believe what we say, make scientific and engineering jobs, engineering profession, something that the country values. We don't do that. Just recently, I participated in a study that looked at what to do about the science, technology, engineering, and mathematics manpower in this country. How come we are not graduating more people with this kind of degrees? And the group had, and I think Professor Mahajan, I think you were there for the first meeting. My only comment was, we just have the wrong, you're asking the wrong question. Right question to ask is not what we can do in the area of education to make that change. The society has to start valuing this kind of people better than what they do. I live in Los Angeles area. We have number of defense aerospace companies. And every few years, there is a layoff of 1,000 people from one company or other because they lost this contract or that contract or what have you. What message does it send to young people? What it says is that you are expendable. If you work as a technologist, you are expendable. You are no longer a resource that a company or the country values. And until we change that, we will not come out of this current problem. We'll always be there, and nothing else you can do. I know I didn't answer your question, but I answered the question the way I think something that people need to pay attention to, which is we have created a social scheme of things which is not exactly conducive to getting things done right.
We have time for one or two more questions. Bruce?
Could there ever be another Bell Lab?
Okay, so will there ever be another Bell Labs? The answer is probably no. And by probably, I mean to a very large certainty there will not be. And I think that you have to look at why, and you probably know why, but one should understand why Bell Labs was what it was and why it was able to do the kind of things it was able to do. There are two critical parameters. One is the kind of funding that was available, which was funding that came out, and probably most people don't know. It was 0.1 cent on every single phone call that was made in the United States. That's the royalty that they collected that went back to the research area in Bell Labs. It doesn't sound like very much, but when you consider how many phone calls were made, that made a lot of money. So that level of unrestricted funding, which had some great value. The second thing was the way research was managed, and I think that probably was of significantly greater importance. As Dean Lavergne has mentioned earlier, one of the characteristics of Bell Labs was you always hired people smarter than those around you. I mean, that was an absolute critical requirement. Because if you do that, what I call you spiral yourself up in the quality rather than spiral yourself down. Because anytime one is afraid of a new person coming in, being smarter than you are, you know the message that you have created. So that's number 2. And number 3 was, as I mentioned earlier, it was not blue sky research. It was research in an area that in the long term was going to benefit AT&T, which was a regulated monopoly whose job was to create the next generation and the one after the next generation communication technology. So much of it is focused towards that. There are some outliers, but by and large, that scheme worked. I can't imagine any company, or certainly not country, putting up at the height of in the heyday of Bell Labs, the research establishment there probably was something close to $500 million a year establishment. Anybody putting up that kind of money with the notion that I'll come back in 10 years and ask you what you have done. It just won't happen. Which is a shame because, and again, I think let's be very honest, the demise of Bell Labs had only partly to do with what Judge Green did. It had a lot to do with how AT&T managed itself. And think about it. That's very, very critical. Had AT&T been managed better than what it was from 1983 to 1995, the outcome could have been different.
So perhaps we have time for one last question from the audience.
I wanted to know if you have any advice for educators like us of what we can do to improve the innovation level of our students.
Repeat the question.
Advice as to how to improve the innovation level of our students for educators.
Innovation level of?
Students.
Students, okay. I think we need to somehow rethink, and again, I don't consider myself a true education person. I mean, I teach at UCLA, but I've spent only very few years doing that. I think the critical point is to be able to be an innovator, you have to be able to think. The thinking requires not only understanding what you have been taught, but also how it applies to the world around you. And so the notion of solving a problem should be instilled in young people at an early age. Not just learning, but give them free time to think about problems that need to be solved. 99% of the times they may pick the wrong problem, but that's where education, good education, can help, which is teach young people to distinguish between good and not so good problems. There is no such thing as a bad problem. The only solutions are bad. Problems are always good. So the question is good and not so good. One of the things that I used to insist when a new person came into Bell Labs is think of something that you haven't done for your PhD dissertation. Because I don't want you to repeat that. I want you to go out and think about problems that you can apply your education to, your training to, thereby get on a different path of what you need to solve that problem. If there is a reason to believe that there is a problem that needs to be solved, if you don't have the tools to do that, you will develop the tools. You'll get to the point where you will, in fact, create the infrastructure, whether it's knowledge, whether it is innovation, whether it is ideas, to solve that problem. So how do we couple problem-solving skills with education that we impart? I don't know how to do that, but I think that's something, if it can be done, one can significantly increase innovation that young people are able to bring forth.
Well, please join me in thanking Dr. Patel for an absolutely delightful conversation. Now, I'd like to invite everyone to join us for the next speaker in the Chancellor's Colloquium series, Brailine Shitsunge, who will be here next Tuesday, February the 5th at 4 p.m. And he is an internationally acclaimed expert and facilitator of the Nigeria-South Africa group on agriculture. So please join us. It'll be fascinating. And also join us now in the lobby for a reception so you can continue the conversation with Dr. Patel. Have a great evening.